Okay, welcome back, room. So today I'm going to do a video on proving Euler's criterion, and I'm going to give you Euler's criterion right now. So what Euler's criterion states is that if we have some residue A, the legendre of A is congruent to A to the p minus 1 over 2 mod p, where p is an odd prime. Okay. And again, if it is an even prime, which is just going to be 2, we're going to get some strange squared business. So a to the 1/2 here, which we don't really want to deal with. Okay, well, how do we go about proving this? Well, first, I'm going to consider 3 cases. The motivation of which being the Legendre symbol and how it's defined. So notice that it gives different values for whether the residue A is a quadratic residue, a not quadratic non-residue, and 0, or multiple of the modulus. So let's split up into those 3 cases. First, let's consider the trivial case, where A is congruent. So case 1, A is congruent to 0 mod p. So let's look at that case. Well, we can just directly see what this gives us. Notice that if we plug in 0 here, well, we're just going to get 0 to this power, which is just 0. And notice that the Legendre symbol of 0 is going to be 0 by definition. And therefore, well, we just get that 0 is congruent to 0, which checks out. Okay? So case 2, let's see. So A is a quadratic residue. Okay, let's look at that case. So when A is a quadratic residue, notice that by our previous video, which you should watch if you have not yet learned about quadratic residues, if we note that G is some primitive root, mod p, we're going to get that we can write A as being congruent to an even power of the primitive root, G. So we have equals G to some 2k, where k is some non-negative integer, mod p. Okay, well, let's plug that into here. So notice that we're working from this side to this side and trying to extrapolate if these are equal. So, well, let's see. So when we plug that in again, we're going to get that g to the 2k to the p minus 1 to the 1 over 2. I'll just write that out to be clear. So we're going to get g to the 2k all to the p minus 1 over 2. Right? We can't forget the parentheses. But notice that that's congruent, or it's basically just equal to. We're not using any congruence facts in this manipulation. Well, if we just multiply the powers, we're just going to get g to the k times p minus 1 mod p. How is this useful? Well, we can just make use of Euler's theorem, as we have throughout all of these past number theory videos, pretty much. So notice that, again, p minus 1 is 5p, and therefore g to the p minus 1 is going to be congruent to 1 mod p. And if we just raise that to the kth power, that's still 1. So in other words, this is congruent to 1 mod p. But notice that if we plug in a quadratic residue into the Legendre symbol, it's also 1, so it checks out. Okay, case 3. Okay, so let's see. So if A is a quadratic non-residue, this is just a little bit more tricky. There are actually a few ways of going about this. Originally, I came up with a rather strange and inefficient way, but since we've already proven the fact that I'm about to use in a previous video, then, well, why don't we just use that? So what I'm going to do here, and I'll leave it as an exercise to you to find a different way to solve this, to consider this case. So first, with both cases, we can just obviously take, this obviously just implies that, again, by the previous video, A can be written as the generator, or I mean the primitive root, to an odd power. Call it g to the 2k plus 1. And since we're dealing with different cases, we don't have to worry about these k's overlapping. Okay? Okay, well, what happens when we plug that into here? Well, first I would like to separate this out as g to the 2k times g to utilize the nice property when we multiply 2k times p minus 1 over 2. And what happens there is, well, whenever we distribute the power as such and multiply, we're just going to get, well, notice that by plugging in, we're going to get g to the, well, 2k times p minus 1 over 2 is just k times p minus 1 over p minus 1 times, well, g to the p minus 1 over 2 mod p. And again, by the same reasoning as here, this goes to 1 mod p. And this part, well, using a fact that we proved in the previous number 3 video, this is actually going to be congruent to -1 mod p. So that's exactly what we showed in a previous video. And just to recap a bit, if you don't want to switch to that video, if we look at the circle diagram that we analyzed in that video on primitive roots, well, notice that on this diagonal, the diagonal represents all of the values where the values there are their own inverses. So, and we notice that, well, here we're clearly going to get a g to the 0, then some stuff here, but here we're going to get g to the p minus 1 over 2, because we have to go around to the halfway point, right? Okay. Well, let's see. So, and again, just as review, we can check that this works, that it's its own inverse, by computing this squared, which is just g to the p minus 1, which is congruent to 1 mod p. So that's good. And, well, furthermore, we extrapolated that this has to be -1 mod p, because by definition, what it means for some residue x, or some value x, to be its own inverse, we need x times x to be congruent to 1 mod p. But that implies that x squared has to be congruent to 1 mod p. But that just tells us that by subtracting 1 on both sides and using difference of squares, we're going to get x plus 1, x minus 1 has to be congruent to 0 mod p. And using the fact that p is a prime, p divide either x is congruent to -1 or x is congruent to 1 mod p. But we've already accounted for the case where x is congruent to 0, where x is congruent to 1 mod p. And, well, since these have to be distinct mod p, they generate all of the residues, non-zero residues mod p. This has to be -1 mod p. So therefore, this is going to be -1 mod p. But that completes our proof, because if we plug in a quadratic non-residue into our Legendre symbol, we get -1 as well. So this case is a check mark. Okay, well, that's it for Euler's criterion. Again, we're going to be using this briefly in a proof for our next video. And I just think it's a nice little exercise. The proof of it is a nice exercise to review what we learned about quadratic residues and primitive roots. So I think it's a pretty good conclusion problem for those two. So I hope you really enjoyed, and that is it for this video. I'll see you again shortly in the next video.